Okie doke. There we go. All right, Chemistry 102. We've covered all of Chapter 15. I didn't lecture on Section 15.5 tonight, but I have that on a video in my YouTube channel. I posted it to the chat, and you can also find the link to the Chapter 15 playlist that I have posted in the announcements in D2L. And so we're going to try some practice problems from Chapter 15, and we're going to start with question 15.17 or 15.17. And it simply asks us, for each pair of compounds, predict which would have greater solubility in water and explain. So we're talking about solubility in H2O. And in A, we're asked to compare hexane. So we're comparing hexane to 1-pentanamine. So 1-pentanamine. All right, 1-pentanamine and hexane. Let's start by drawing hexane. Hexane is a hydrocarbon with 1, 2, 3, 4, 5, 6 carbons. 1-pentanamine is when I have 1, 2, 3, 4, 5 carbons, and then I have an amine on the first one. Now, this is not meant to be a trick question or a mind boggler. Can anybody tell me which one of these two compounds would have a higher solubility in water?
Pentanamine.
Yeah, can you explain why?
Because it's the N bonded with the H hydrogen bond.
Exactly. It's 1-pentanamine, and it's because it has hydrogen bonding, right? The only intermolecular forces that will be experienced, the hydrocarbon hexane is non-polar, and water is polar, and we know the rule that like dissolves like, and so a hydrocarbon like hexane is not going to dissolve in water. Whereas pentanamine, as Gavin says, it's also somewhat polar, right? This part of the molecule is polar, right? So polar, and also can form hydrogen bonds, right? If you were to draw a molecule of 1-pentanamine, let's say, like this, and draw out the nitrogen-hydrogen bonds, okay, you could represent a hydrogen bond, with a water molecule like this, where you draw a hydrogen bond maybe between the delta negative, the lone pair on the nitrogen, and the delta plus on the hydrogen, or you could draw a hydrogen bond like that. Okay, so the answer is 1-pentanamine will be more soluble in water, and I think we figured that one out. The next one is sorry, I'm reading the wrong question. Cyclopentane or 2-butanamine. So if we have cyclopentane, okay, or 2-butanamine, so we have 1, 2, 3, 4, we have 2-butanamine. The answer is going to be the 2-butanamine, and the reason is the exact same as it is in A, right? The hydrocarbon is completely non-polar, and not only is this region of the molecule polar, but we say polar, and it can also form hydrogen bonds, okay? So hydrogen bonding with that primary amine. All right, well, let's take a look at question number 21. Just need to flip over here. So this is question 21, and this is nothing more than doing some IUPAC nomenclature. When asked for a systematic name, that systematic means the same thing as an IUPAC name. So we have question 15.21, and we just need to provide IUPAC name. So we'll start with A. I'm going to draw the bond line structure. So 1, 2, 3. Okay. In the book, they have them drawn as condensed structures, condensed structural formulas, but I'm going to draw I'm just going to draw them as bond line structures. It's just simpler. And we'll try these ones right here. These the first three. I'll give them the all college try. I'll give you a second to take a look at the first one, see if you can come up with a name. In fact, if anybody has a name for the first one, Or the second one? Or even the third one? Well, let's go over the first one together. The first thing that we do is we want to find the longest hydrocarbon chain that contains the carbon with the nitrogen on it. So that would be 1, 2, 3, 4 carbons like that. That's our longest hydrocarbon chain. And we want to number that chain in such a way that we give the carbon with the nitrogen on it the lowest possible number. That means we'd have to start numbering here, right? 1, 2, 3, 4. Like this. If we had started over here, then this carbon would have the number 3. 2 is lower than 3, so this is the correct way. Now, the parent here has 4 carbons, so that would be butane, okay? But what do? We drop the E off of the end and we replace it with amine. And so since our amino group is at carbon 2, this would become 2-butane amine. Let's try the same strategy on the next one. Our longest carbon chain, I think, is pretty clear on this one. It's 1, 2, 3, 4, 5, 6 carbons. I'm going to number that chain in such a way that I give the carbon with the nitrogen on it the lowest possible number. Should I start numbering this carbon chain from the left or from the right?
From the right side.
Yeah, it's B from the right side. Okay, because if I was to go from this side, I'd have 1, 2, 3, 4. Right, I'd have number 4 for the carbon with the nitrogen on it. But if I start going from the right-hand side, then I have 1, 2, 3. 3 is lower than 4, so this would be the correct way. So if I have a hexane derivative, I drop the E, and this becomes hexanamine. And my amino group is on the third carbon, so this would be 3-hexane. Come on, hexanamine. 3-hexanamine. The next one, I'll go over it kind of quickly here. The parent is a cyclopentane, right? If you just have a 5-carbon hydrocarbon like this is cyclopentane. We do not have to provide a number for the carbon or a locant. We call a locant. We don't have to call it 1-cyclopentanamine because if there's only one substituent, the carbon is de facto going to be number 1. So we cross off the E, and this molecule becomes cyclopentanamine, like that. Let's try one that I'm just going to make up for you, okay? What if you had something like this? Can anybody come up with a name for this compound? Give you a second to think about it. And if you even if you have a guess, just a guess, throw it out there. All right, let's take a look at it. I think you're in the right vein there, Gavin. Let's take a look. The longest carbon chain has 1, 2, 3, 4 carbons, right? Gavin said the parent is a butanamine. He's absolutely correct. Okay, 100% correct. All right, so if this is our longest carbon chain, well, we're going to number it in such a way that we give the carbon with the amine the lowest possible number. So we'd go 1, 2, 3, 4, right? This gives our amine the lowest possible number. And so on the third carbon, we have a methyl group, right? A CH3. So this molecule is 3-methyl 2-butanamine as our parent. Butanamine. Does that clear it up? For my students? Okay, good. All right. There we go. Yeah, sometimes when they have branches, they get a little bit more complex. Go ahead.
I had a question on A in 15.21.
Yeah.
So why did you not consider the, I guess, like next to the NH2, there's what looks like a methyl group. Why is it not seen that way in this particular one? And
Why
seen?
is this not a
Yeah.
methyl group, for example?
Yes.
Yeah, okay. Because the rules state, okay? I
Uh-huh.
mean, if we were just talking about this group, Haley, we'd say, yeah, that's a methyl group, no problem. We could call that a methyl group. But the rules for nomenclature are as such, okay? If we redraw our molecule like this, the rules are, rule number 1 is you find the longest parent chain, the
Yeah.
longest carbon chain that has to contain or has to have the carbon with the nitrogen on it, right? So all of this is a continuous chain. Does that
Okay.
make sense? So if you have a 4-carbon hydrocarbon, right? If you have just 1, 2, 3, 4 carbons, that's called butane. So that means that this is some kind of butane amine. Those are just the rules, okay? That this is some kind of butanamine. And since the amino group is at carbon number 2, it becomes 2-butanamine. Does that help?
Yes. It just looks, it looks kind of different from, like, I think what I've seen before. I know the longest chain is what we're looking for.
Mm-hmm.
But to include that, I guess my brain just doesn't see that that's like included
Yeah.
within the longest chain.
Well, what if you had something like this, okay? If you had a molecule that looked like this, how would you name this compound? Well, the longest carbon chain that contains the carbon with the nitrogen on it has 1, 2, 3, 4 carbons. So this is still a butanamine, right? This is still some kind of butanamine, okay? And it's some kind of 2-butanamine, right? Because our carbon chain goes 1, 2, 3, 4. So this is some kind of 2-butanamine, but on carbon number 2, we also have a methyl. Okay?
Yes.
That's not part of the parent chain. So this would be 2-methyl, 2-butanamine. Okay? Whereas in this example here, this is part of the whole chain. Does that help?
Yeah, that's part of the whole chain, but the amine group is on carbon 2, right? Just
Correct.
on. Okay.
Correct. Yeah.
Okay. Thank
All
you.
right. No problem at all. All right. Well, let's take a look at, where are we? That was question 21. I wanted to look at question 23. So moving right along. In this one here, we're just going to practice drawing our bond line structure. So draw structure. We'll just put draw structure. I prefer when my students draw bond line structures. If you have to draw a condensed structure, hey, one of my students asked me, is it okay if I draw this kind of structure? Unless the lab manual is like very specific that she wants a very specific structure, as long as your structure is correct, Mr. Dion is going to be a happy camper, and so will you be, right? That's the main thing. You just want it to be right. Okay, so if we look at 15.23, let's give a few of these a try. Let's see. A is diethyl amine. We'll try A. We'll try C, which is 3. And we'll try E, which is triphenol. All right, let's try all 3 of these. I'll give you a second. If you want to do a bonus, it could be B2, homo, 2, pentane. I'm going to give you a second to try drawing these. Give you a minute or so. All right. Let's take a look at the first one. These are kind of hard for me to ask. Okay. Yes, we'll take a look at some secondary and tertiary for sure. The first one is diethylamine. So we'll start by putting a nitrogen. It's going to have two ethyl groups. So we have an ethyl group here. We have another ethyl group there. This is a secondary amine. And so there we go, like that. Let's see. The next one is 3-decanamine. So if you have decanamine, it means you've got 10 carbons in your chain. So look, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if we number these, 1, 2, 3, so on and so forth, like that. On the third carbon, we should have our amino group. So we have 1, 2, 3, and we have our amino group like that. So that's 3-decanamine. Okay. Can anybody tell me what a phenyl group is? And the next one we have triphenylamine. Can anybody tell me what a phenyl is? And it's not a trick.
Is it one less hydrogen off the benzene ring?
Yeah, it's a benzene ring that's a substituent, right?
A
So if you have
substituent.
this, let's say this is a methyl, then if you have a benzene ring as a substituent, okay, that's a phenyl. So this is a methyl, and this is just a comparison here, a methyl and a phenyl, like that. Okay, so we've got an amine, and it's attached to 1, 2, 3 phenyl groups. So we have a phenyl group here, we have a phenyl group here, and we have a third phenyl group here. You might be wondering, wow, that's pretty annoying to have to draw all of that. There's an easier way. For a phenyl, sometimes chemists just call it a pH with a capital P and a lowercase h, not to get it confused with pH, which is a measure of the concentration of hydrogens. Okay, like that. The next one is 3-bromo-2-pentanamine. So this is some kind of pentanamine. So we have 1, 2, 3, 4, 5 carbons. We can number them out, 1, 2, 3, 4, 5. On the second one, we have an amine. And on the third one, we have a bromine. Yeah, so 3-bromo-2-pentanamine. Yeah, if you want to try some, give back name. Let's try something like this. Let's say we have this. Okay. Or something like this. Or let's see this. Okay, I want you to give the IUPAC names of these, not the common names, the IUPAC names. Sadie, this is what you meant, right? You want to do nomenclature of a secondary or tertiary? Here we have a tertiary, here we have a tertiary, and here we have a secondary. All right, so give them a shot. Give you a few more seconds. All right, let's take a look at the first one. And the parent of the first one would be, yeah, you got the second one, right? Let's do the first one. So the first one, the parent here would be an aniline, right? Right, if you have this molecule like this, this is aniline. And so the name of this molecule would be NN-dimethyl aniline. So NN-dimethyl because you get two methyls on the nitrogen. Aniline. Yeah, and Sadie, your answer, I think it's Sadie who put it. Yeah, absolutely. So Sadie put for the second one, the parent is going to be the 4 carbons here. So that would be 1 butanamine. So it's NN-diethyl 1 butanamine. So NN-diethyl 1 butane. And if you're wondering, well, why is the 1 important? Let me show you, in case you don't follow me. Let's say you had this, right? If you had this, the parent would still be a butane, and you have NN-diethyl, but this would be 1, 2. This would be NN-diethyl 2 butanamine. Okay, so there's a difference between these two. All right, and the last one. Oops. Here, there we go. The last one, its name, we got another secondary amine. Again, the parent would be the 2 carbons. So this is some kind of ethanamine. So it's got a methyl group on it. So this is N-methyl ethanamine. And that's it, man. There we go. All right, let's try. Where was I? I don't remember. Question 23. Did we do that one? Yep. Let's do question 25. Draw condensed formulas. Let's try some reactions. Okay. Let's try question 15.3. Let's try question 15.34 because it's not one of the ones I asked. Go over it. Oops. 15.34. These are just some good reactions that help you to get some practice. So we have ethanamine plus water gives us. Okay, so you need to fill out what's the question mark. While you're working on that one, I'll write down B. So all right. Okay, well, let's take a look at the first one, 15.34a. And what's going on in this reaction? We have ethylamine. This is ethylamine, and then we put ethylamine in water. And what does it do? Well, ethylamine is a base. And remember that water can behave as an acid or a base depending on the situation. Okay, water is never a strong acid or a strong base, but it can behave like an acid. It can donate a proton, and it can behave like a base. It can accept a proton depending on the situation. And so water here is going to behave as an acid. What does an acid do? An acid donates a proton, and a base accepts a proton. Okay, so if the base is going to accept a proton, after the water loses a proton, you're left over with OH minus. So that means what you're going to have here will be the amine, but with 1 extra hydrogen. And the extra hydrogen is going to be on the nitrogen, so it will have a positive charge. Okay, the next one says something plus HCl gives us this ammonium chloride, or alkyl ammonium chloride salt. So what would it be? Well, if we're adding HCl to it, HCl is an acid. And so we need to have some kind of base, and our base is going to be an amine. So our base is going to look like this. It's going to have NH with the two propyl groups, one here and one here, 2, 3, 2, like that. So if we take the amine, so this is dipropylamine plus HCl, we end up with the alkyl ammonium salt. Why? Because we draw HCl like this, what happens is the lone pair on the nitrogen, is going to form a bond with the hydrogen, and the pair of electrons here are going to go onto the chlorine to make a chloride. Okay, the next one is an amine plus water. This is my bond line structure. I'll clean it up a little bit here. So you have a methyl group and an isopropyl group. So it's isopropyl methylamine plus water gives you what? Well, again, we know that an amine is a base and water will behave like an acid. And so the pair of electrons on the nitrogen is going to take the hydrogen, right? Because a base is a proton acceptor. And we're going to use the water as an acid. It's going to donate the proton. So what we're going to be left over with is the amine, but with an extra hydrogen. And so it's going to have a positive charge. And then we'll also be left over with a hydroxide ion. All right, and the last one is ammonia, which is a base. Okay, ammonia is a base. It's a weak base, but it's a base. And hydrobromic acid is most definitely an acid. What happens when you add an acid and a base? They're going to neutralize each other. And as always, the lone pair on the nitrogen is going to take the hydrogen because a base is an H plus acceptor. Okay, and an acid is a H plus donor. It's also going to take those electrons, and so I'm going to be left over with NH4 plus, which is an ammonium ion, and bromide, like that. So I'll be left over with ammonium bromide as a salt. Okay, everybody feeling a little more confident about their acid-base chemistry after that? John, no? Do you want to do more practice on that, or can we move on to something else? All right, good. Thanks, Gavin. That's great. Glad that things are going better. Okay, just let me see. There's some other questions I wanted to throw out here. Some of these questions are kind of open-ended a little bit, but whatever. Let's try a little bit of 15.31. So we're going to back up a little bit here and take a look at 15.31. I don't really relish the way they ask this question. It just says, write an equation to show a reaction that would produce each of the following products. So it's saying, you know, if you wanted to make this compound here, okay, and we looked at this during the last lecture, this one here, this is called paratoluamide. How would you make that? Well, if you remember in our last lecture, there's only one way that we learned how to make an aniline derivative, right? Because this is an aniline, type molecule. And the only way that we learned how to do that was to start with a nitro. Okay, so you start with the nitro group instead of the amine, and then all you have to do is a reduction. So you put a hydrogen inside square brackets like that, and this means a reduction, right? Loss of oxygen and gain of hydrogen, and that will reduce the nitro to the primary amine, and you'll end up with your aniline derivative like that. Okay, and it's the same for all of them. Like, or is it the same for all of them? Let me take a quick peek here at them. Yeah, let's take a look at B. Take a quick look at B. And I also want to take a look at D. So just give me a second here. B. So I want you to show me how you would make this compound. I want to make this compound. And then in D, if you wanted to make this compound. All right, I'll give you a second to try to write down your answers, and then we'll take a gander at these. Okay, so for the second one, since it's an aniline derivative, you would do basically the same thing. You'd start out with the nitro group instead of the amine, and you would treat that with reduction conditions, and that would reduce the nitro to the amine, and so that is how you would do that one. This last one here, it just kind of caught my eye because we talked about the reaction last class, but we went over it pretty quickly. So how would you make a primary amine like this? You wouldn't make it from a nitro. Okay, this wouldn't work. The best way to use a nitro reduction is on an aromatic ring. So we'll put here NO2 reduction is, or we'll put works best on aromatic ring. So what I mean is this. If you tried to say, well, I'll just take this compound and I'll have CH2 and then I'll have nitro and then I'll reduce that, okay, using hydrogenation or something, it won't work. Okay? It doesn't work when you try to do that. So there is another way. And the way that we looked at, which might not have caught your eye as much on Monday's class, is that we use an amide. Okay? If we have an amide, primary amide here, we can reduce that where we burn off the oxygen, so to speak, and replace it with two hydrogens, and then we would end up with CH2 and, oops, make that prettier, and H2. Okay, so reduction of an amide using reduction conditions or reduction of a nitro on an aromatic ring. All right. Sec. Let's take a look at 15.47. This is a conceptual question. 15.47 is why do amides have such high boiling points? Can anybody tell me the reason why amides have really high boiling points? Something very specific that we looked at this evening. Yeah, exactly. So Gavin, you're totally right that it is because amides have a carbonyl, so they have a strong delta minus on the oxygen, and then they have the nitrogen with the two hydrogens, and they have a strong delta plus on these, okay? And so if I have a second molecule of an amide, okay, it's going to be able to form hydrogen bonds like this between the oxygen on the carbonyl and the hydrogen on the nitrogen, okay? So we'll put here strong hydrogen bonds between oxygen of the carbonyl and hydrogen of the nitrogen-hydrogen bond. Okay, so that's the reason why amides have such high boiling points. Let's see. Let's try some IUPAC nomenclature of amides. Okay. Is there any common ones? Let's try 15.54. So this is question 15.54. And it just says nothing more than give the IUPAC name. So give IUPAC name for these molecules. I'm going to draw them out as bond line structures just because it's a lot faster. So if we have this, come on, go. This. There we go. So this will be A. And then B, we have this. Go. Let's see, we have this one. All right. So I'll give you a few seconds to look at these ones. Six. All right. Well, let's take a look at the first one. So this is some kind of amide. Remember, if we were to have the carboxylic acid, so with 1, 2, 3, 4, 5 carbons, this would be pentanoic acid. We remove oic acid and we replace it with amide, pentanamide. So this is some kind of pentanamide. And we have a bromine at carbon 1, 2, 3. So this is 3-bromo pentanamide. 3-bromo pentanamide. Okay, let's take a look at the next one. If we had a 3-carbon carboxylic acid, and again, it's only asking for IUPAC names, that would be propanoic acid. So we scratch oic acid and we get propanamide. And then we have a methyl on carbon 1, 2, on carbon 2. So this becomes 2-methyl propanamide. Okay. And the last one is a benzoic acid. Shit, did I put a benzoic acid there when I meant to put an amide? Different chapter, isn't it? Sorry about that. Okay, I had carboxylic acids on the brain, I guess. Anyhow, you all know what carboxylic acid this is. This is benzoic acid. So benzoic acid. So if I remove oic acid and replace it with amide, this must be some kind of benzamide. So benzamide. And if I count the carbons, starting with this carbon here, 1, 2, 3, this is some kind of, or this is 3-bromo benzamide. 3-bromo benzamide. There we go. I want to bump up all the way to question 15.67. So question 15.67, which is kind of some fill in the blanks that involve amide chemistry. So here, 15.67. All right. So hopefully in your textbook, because it's going to take me a second to write all these out. I'm going to draw them as bond line structures just to make life a little easier. So plus something. All right, I'll give you a couple of minutes to think about these. All right, let's take a look at 15.67a. So I'm starting off with an amide, and I'm treating it with acid. And so what this is going to produce, or what the result will be hydrolysis of an amide in acid. Okay, so if I'm hydrolyzing the amide in acid, this is the amide bond. That's going to get broken. So I'm going to end up with this piece, and I'm also going to be left over with this piece. Now I need to finish these off. Now, since an amide comes from a carboxylic acid piece and the amine piece, it stands to reason that the carboxylic acid is going to be a carboxylic acid because we're in acid. And so I'm going to end up with acetic acid. But my amine is not going to be methylamine. It's going to be the methyl ammonium ion, right? It's not going to be NH2, right? That would be methylamine. I'm in acid, so that's going to protonate the amine. And I'm going to have NH3, and the nitrogen is going to have a positive charge. Remember that nitrogen normally has 3 bonds in 1 lone pair. Then the nitrogen has a charge of 0. When nitrogen has 4 bonds and no lone pairs, it has a charge of +1. All right. The next one is the exact same thing. It's the hydrolysis of an amide in acid. However, this time we're asked to provide the amide that comes from butanoic acid and methylammonium. So if it's butanoic acid and methylammonium, then we're going to have N-methyl butanamide. So we're going to have our 1, 2, 3, 4 carbons. We're going to have a bond to nitrogen, and then it's only going to have a methyl group on it. So we're going to need a hydrogen here. Let me just move my hydronium over a little bit to make it a little neater. And there you go. So you start with N-methyl butanamide, and you hydrolyze that in acid, and you end up with butanoic acid and the methylammonium ion. All right. The next one is also a hydrolysis reaction. Now, we're missing 2 of the components here. We're missing one of the reactants and one of the products. Now, is this hydrolysis an acid or a base? Well, if I'm ending up with a carboxylic acid, it must be an acid. So I'm going to add H3O plus. This is the amide bond that's going to be broken. So I'm going to have nitrogen with my ethyl group. It's not going to be ethylamine. It's going to be ethyl ammonium. The ethyl ammonium ion like that. Okay? If we were to do a reaction like that in base, okay, like let's say we were to take, you know, this amide, okay, like this, and then we were to put that in base, okay, to hydrolyze it. What would we end up with then? We're still going to break the amide bond, right? So we're going to end up with this piece and this piece. But now we need to figure out what else we're going to have. Since we're in base, we're not going to have a carboxylic acid. We're going to have a carboxylate. But since we're in base, we're going to end up with our amine instead of an alkyl ammonium. And so we would end up with our amine like that. The only thing that's left out of here that would be included some of the time in our book is the spectator ion, right? So let's say instead of using just hydroxide, if they write something like, you know, sodium hydroxide, well, in that case, you'd have the sodium cation next to the negative charge like that, okay? So again, this would be the hydrolysis of an amide in base. All right, you need to know the difference between hydrolysis of an amide in acid and in base. Let's take a look at one more question. I wanted to take a look at question 15.60. So let's see here, 15.60 from our textbook. It says when an acid anhydride and an amine are condensed, an amide is formed. This approach can be used to synthesize acetaminophen, the active ingredient in Tylenol. Using the reactants provided here, draw the structure of the amide product, acetaminophen. So we're starting out with this compound, which is called acetic anhydride, right? We learned that when we talked about anhydride nomenclature, and we're going to use 2 molecules of this aniline derivative here. Okay, like this. So remember what I told you, that the lone pair on the nitrogen is going to attack one of these carbons like this, but it hits it so hard that you're going to lose this part of this molecule. Okay, what would you end up with after that? Let me show you. You would have this part right here, but then you'd have it bound to a nitrogen with 2 hydrogens and the aromatic ring, okay, with the hydroxyl group. Now that nitrogen is going to have a positive charge. You'd also be left over with an acetate ion, like that. So now what's going to happen is this is the first molecule of the base. Now a second molecule of the base, so I'll draw it out again. The second molecule of the base is going to behave as a base, and it's going to rip off this proton here, which is going to give me overall what? I'm going to have my Tylenol, okay, like this. This is the structure of Tylenol. I'm going to end up with the anilinium instead of an alkyl ammonium. This is called an anilinium, like that. And I'm also going to be left over with the acetate ion, like that. Okay, so that's the formation of an amide from an acid anhydride and an amine. Okay, and make sure you can do the same kind of reaction but using an acid chloride instead of an acid anhydride.